saw in the program that the last talk was also about gentle algebras, but probably about different aspects. So I want to connect these semi-orthogonal decompositions to some kind of geometric/combinatorial models. And I hope to prepare slides, but in the end there were so many diagrams that I stayed with handwritten notes, so I hope you can read it. So if you were there before, this was probably told, but if you weren't, then what are gentle algebras quickly? So this is a certain class of finite dimensional algebras, right? So on one hand, they are quite special, but on the other hand, they are, because this is quite a rich class, so one can test various problems on them. And so there is some finite quiver, and there are some relations. So they are generated by some collection of paths of length 2. And the configuration is rather special. So basically, the quiver and the relations around each vertex, they should look like this, right? So there are at most 2 arrows coming in, at most 2 arrows coming out, and there are relations configured like that. Or some arrows may be missing, and if there is an arrow missing for a relation, so we also discard the relation. So there are some examples of configurations when you erase some arrows and then erase the corresponding relations. Okay, so I hope this is good enough for a definition of this class of algebras. So this is relatively concrete, and the advantage is, of course, that the representation theory is very well understood. So for finite dimensional modules, right? So these gentle algebras are special classes of string algebras, and there is some combinatorial description of all indecomposable modules. But today I want to focus on the derived category much more. Either the category of perfect complexes or the bounded derived category, and this is also understood, and I want to get there step by step. Along with some graphical dictionary, how to draw these representations as arcs into some surface, which sometimes gives more insight. And a little bit of warning. So the basic picture for gentle algebras was this, but the arrows may not be technically different. So some arrows in this picture may be actually twice the same arrow drawn. So what can happen is a situation like that. Okay, so this outgoing and incoming arrows are the same. Okay, and so now maybe I can give you some concrete examples on which I can illustrate the concepts. So what are gentle algebras, right? So the simplest are Dynkin path algebras of Dynkin diagrams of type A, right? So they are all gentle regardless of the orientation, but I chose the easiest situation. Or we can have for example, algebra of type A modulo the radical square, right? So we factor out the compositions of all paths of length 2, right? So this actually it's pretty well known that 1 and 2 are derived equivalent. And in fact, what this is a result, I think, of Schreier and Zimmermann, that an algebra derived equivalent to a gentle algebra is again gentle. So this is no coincidence, but okay, we can illustrate some phenomena quite explicitly. So the Kronecker algebra is also a gentle algebra, right? So we have from the first vertex, we have 2 arrows going out and no arrows going in. And we have 2 incoming arrows and no outgoing arrows to the second vertex, right? So it actually also is an instance. So this actually shows the main problem with them. I mean, the definition is relatively intuitive and straightforward, but one needs to see some examples to get some practice, because there are many kind of degenerate cases, right? Like this one or this one. Well, they also appear on some situations like number 4. So, for example, cluster tilted algebras of type AN or AN tilde are gentle. So there are some names of authors. Or we have some other kind of ad hoc examples which will be useful. Like this number 5 was an illustration This is actually related to semiorthogonal decomposition. This was an illustration of the fact that if we have that there is no Jordan-Helder theorem for semiorthogonal decompositions. And I mean, it could be seen also in pictures, which I want to show you. I probably will not have time to do that really, but I will show you the picture for this algebra. So I mean, it could be viewed as some kind of exercise. And we have number 6, and number 6 is also interesting in some way because all the explicit algebras, except for some cases in 4, but all the algebras which are explicitly drawn here, this, and that were of finite global dimension. And so this is an explicit example of something which is of infinite global dimension. So this is actually one case where there is a distinction between perfect complexes and the bounded derived categories. So it will be also useful to illustrate something. And so gentle algebras are in some sense homologically special. I won't go really into that, but I guess many of you know what Gorenstein algebras are. So they have finite injective, the algebra itself has finite injective dimension on the left and on the right, and gentle algebras are such. So they are very far from some generic algebras. They are very special, but as I told, the class is still really rich. Okay, and so I want to get to geometric models. And now there will be a lot of pictures, because the idea what I want to do. So I mean, I want to assign to each algebra some compact-oriented surface with a boundary and some decorations, and I will draw several such surfaces, such that indecomposable objects correspond to certain arcs up to homotopy, and homomorphisms between them correspond to certain crossings of such arcs. In a configuration where the arcs have up to homotopy a minimal possible number of crossings, so every pair of arcs could be configured in such a way. And I'm a bit vague here at the moment, so this is this remark that, or warning that I would need to add some details. And this idea is okay, was recently very intensely explored. So the references, so there is such a representation for module categories by Karin Bauer and Raquel Coelho-Simoes, published in 2021. But actually, it's a preprint comes from 2018, so it's approximately from the same time as a still preprint of Opper, Plamondon, and Schroll, which describes such a dictionary, such a geometric model for derived categories, for bounded derived categories. But then there is also some conceptually very much related, but paper by Hayden, Katsarkov, and Koncevich. They use a bit different techniques. They use infinity algebras, which is actually quite convenient. And they view this geometric model as an instance of homological mirror symmetry. So this surface and the arcs, and so for them is something which is called a partially wrapped Fukaya category. And yeah, the morphisms, the crossings are kind of instances of lower cohomology, but I don't want to go into that. But I mean, the paper is quite dense and contains a lot of information. And okay, some remark before I show. Okay, so here comes my first example. So there is an algorithm. If you have a gentle algebra given by a quiver and relations, so there is an algorithm to construct the surface with some decorations. Okay, and so I will try to explain the idea of examples, because the formal definitions, you can find it in the references which I gave, and I will send. I will make these notes available so you can find the papers. And so my first example is the algebra of Dynkin type A5, right? So the first surface is just a disk, and there are some decorations. So the vertices of the algebra will correspond to some arcs, so the green arcs here, okay? And the green arcs cannot be just randomly placed in the surface. So on the boundary of the surface, there are some green dots, right? And the arcs could end, which correspond to the vertices, only in the green dots, right? And there is some rule. I mean, there are several such models that makes it a bit messy. In the literature, there are some variants which are typically equivalent, right? But for technical reasons, in between every pair of green dots on the boundary, I will place always a red dot. So we have now how many? 6 green dots and 6 red dots on the boundary, and the surface is just a disk, and I need to keep some orientation, right? So I will. So when I go around, for example, this green dot here, green vertex, where all the arcs join. So when I want to, I will go in the positive direction. For me will be counterclockwise for this talk. I hope I'm able to be consistent, right? And so whenever you see an angle of 2 arcs, so you draw an arrow, and if you follow this rule, so you recover back your quiver, right? One thing, so what these arcs also could mean. So if I work, for example, with right modules, so indecomposable projectives correspond to vertices, right? And if I work with right modules, so the maps between indecomposable projectives correspond to just paths. Okay, so I can also view these green arcs as indecomposable projectives, and these arrows then stand for some generating morphisms, right, between the projectives, which correspond to arrows here. And now I can tell a bit more about how these, if you want. So what are the red dots good for? I see a question. Okay, I will try to explain it, because the red dots are related to how you actually get the polygon, right? If you want to glue it from the surface, if you want to glue it from polygons. So I have the red dots, and I have some configuration of green arcs. And then I can draw a configuration of red arcs in such a way that they end at red dots, and every red arc crosses exactly one green arc. And so this is the collection.
Yes? There is a question in the chat. Can you?
Yes, there was a question what the red dots are good for. And I'm trying to explain that now. So basically, what you can do, you can draw such a dual configuration of red arcs, and basically, if you cut the polygon, the surface along red arcs, you get some polygons, right? And this would be somehow related to the algorithm how to glue it together. Or, I mean, for people who like it, the gentle algebras are also what is called COSUL. And if you draw the red arcs, you get a COSUL dual. But then there are some technical issues. Sometimes the COSUL dual would not be finite dimensional. So you get something which is called locally gentle algebras. There are some grading issues. But I mean, if you take all that into account, it should work. It will work in the end. But I don't want to go into this direction. Okay, so for me, it's like more like a way to construct the algebra and to count some invariants. Because I told you that these green arcs correspond to indecomposable projectives. So how can you get other objects in DBA? So other objects, okay, so here I try to explain it again on this example once it appears there. Seems to be a bit slow. So if you can, yeah, now it is there, at least for me. So I can consider other arcs from between the green, from one green dot to another, and I want to consider non-trivial such. So that means which are not homotopically homotopic to a point, which are not kind of contractible. And I also want them to have as few intersections with the red arcs as they can, right? So, for example, I don't want to go here and back and do such chaos. And if I draw say this blue arc in such a way, then it crosses some red dots, and each crossing will stand for a projective. And there would be always some morphism, some canonical morphism, say here from P2 to P5. And so this is a bit fast, but in such a way, at least in this particular example, it always works. If you draw an arc connecting two green dots, which is not contractible, then you can get a complex, actually, right? From here, I have one P2 for this crossing, one P25 for this crossing, and one morphism. There is actually just one here up to a scalar multiple, so I don't have to care too much. And this stands for a so this green arc, so this blue arc, sorry, stands for such a complex. And there is one piece of information missing. Yes, the underlying surface, this is another question on the chat, is the disk. So this inside of the disk, right? And the boundary is decorated, exactly. So in this, and I'm missing the grading, right? So I'm missing where these projectives actually sit. And so I actually want to correspond graded arcs. If I have the red decorations, so the red arc, so I can, at each crossing with the red arcs, I can remember the degree, right? These degrees have to follow some rules. So of course, if the degree is here 5, the degree here has to be, say, 6 homologically, right? You can also encode the degree somehow intrinsically via a so-called line field, but I don't think this is completely relevant for these talks, so I will skip it. So I will just consider my surface with some decorations. For example, this with a collection of red arcs satisfying some rules, and a graded arc will be just an arc which remembers some degrees at each crossing with a red arc. Okay. And I mean, you can, if you want, you can make some experiments with that and draw some other arcs here and see what complexes they correspond to. They are not too many, and they will actually correspond to all objects in DBA if you consider the arcs up to homotopy relative to the endpoints. Okay, so now I can be much faster, right? So if I have this algebra, which is derived equivalent, so the surface would be the same. It would be a disk again. So again, the surface will be a derived invariant, so this will be no surprise. But the configuration of the arcs will be a bit different. Okay. And so my green arcs will be now configured in this way. And this has to do with the relations, because there is some rule, right? So if I have maybe, if I have arrows around a point, then there will be no relations between them. Whereas if I have arrows running from one arc to another and then to the next one, then there will be a relation. This is basically the dictionary. You can take it as definition how to reconstruct the equivalent relation from these pictures, right? And so now this algebra with basically all paths of length 2 factored out will be drawn in this way. And if I want to draw the red arcs, so now you see it's a completely dual picture, right? So if I want to draw a collection of red arcs, such that each red arc crosses exactly one green one, so I get this. So the configurations are completely interchanged. And then this is really, for those who know, an illustration of the fact that these two algebras, the last two algebras, are dual to each other. Okay. And then I can again think of objects, right? So I can again take an arc from just a blue arc from one green point to another green point, and it crosses now 4, 3, and 2, and so then I can draw this complex, right? And so in the simple cases, actually in everything which is derived equivalent to DB to an AN quiver, you get a disk and you get just different configurations of arcs, right? To see something more complicated, you can look at the Kronecker algebra. So there the surface is an annulus, right? And you really have two arrows, but now I mean you can see you cannot have really two arrows parallel next to one dot. So to have two arrows, we need two dots, and this is the way it works. It's translated. And then, I mean, this would be the this will be the configuration of red arcs. It will be just this heart-like sign, but upside down. And then if I take this, I can take, for example, another arc, which comes from this green dot to this, but it winds around more. But there is a new phenomenon completely, because the Kronecker algebra is not for finite representation types. There are tubes. Tubes would correspond to closed arcs. And then what complexes this corresponds to? So you see this blue arc here on the left first hits number 2, then number 1, and then number 2 again. So there would be P2, P1, P2, but the arrows actually form a zigzag. And how you interpret the zigzag? So you basically, so the zigzag is something which some people call an unfolded diagram, and then you fold it, right? You put it together. So the complex actually will be that you will have one copy of P1, 2 copies of P2 added, and there will be there will be identity morphism in each component of this map. Okay, so you interpret it like that. So the complex is actually drawn here. So this is the way you can get more complicated complexes, actually, which don't have indecomposable components. And and here, when you have a closed arc inside in the interior, then this is interpreted as some kind of band module. Okay, so this will be responsible for the tubes. So again, I mean, for time reasons, I won't go deeper in that. I mean, you can read in some references which shall give you details, but so that you can have some idea. Okay, so just for illustration, the surfaces can become more complicated. So, for example, for this algebra, the surface is a torus with one disk cut out so that it has a boundary components, and this is the configuration of dots, and I just drew the configuration of green arcs, so they should correspond to vertices of the quiver. So there are 3 if you can locate them, right? So one is this one is going around the torus this way, and the last one is the one which kind of goes around in both directions. And you can draw the arrows there, and you can draw the dual configuration of red arcs and so on. And maybe I want to show you one more phenomenon, because this hasn't appeared yet. What happens if we have infinite global dimension? If we have something of infinite global dimension, we can have red punctures. We can have even red arcs in the interior, right? And the configuration of green arcs here, but also in all the previous examples, should have the property that if you take the green arcs and the boundary components, they should cut the surface to some polygons. And in each polygon, you should have exactly one red arc. So this is another rule which these pictures follow, right? And this is pretty much all. Now I told you everything. And so here, I mean, we have four dots, 4 polygons. 2 of them are outside, but then there are some 2 extra inside, right? So that because otherwise we couldn't implement actually these cycles with full relations in pictures. So the corresponding picture configuration of red arcs is this one. And this also cuts the surface to some polygons. So now the polygon is again a disk, but there is a difference from the previous situation because it has punctures inside, and that also counts. So it's a disk with 2 punctures. So it's a different thing. And if you look, for example, at the dual polygon, which now contains exactly 1 green dot, so there is an edge which actually is folded. Right? It's when you go around the polygon, you meet this edge twice, so it's like it's folded. And in this situation, because the algebra is not finite global dimension, we can have also some complexes in dB which have infinite projective resolutions, and I can tell you what these guys are. So these guys are actually these are arcs which intuitively, either at one or at both ends, wind around some of the puncture, right? So the corresponding complex will be eventually periodic, and it will look like that, or like that here, because here we have again some place where the arrows go in different directions, and so we again fold it. Right? And so this is actually a result about gentle algebras, that every finite dimensional complex, if you look at a minimal projective resolution, so then it will have one or two branches essentially, which will be periodic. So the projective resolution of anything will be the minimum projective resolution of anything in DB will be eventually periodic. So this is something very special. Okay. And now basically this is all about the graphical dictionary, and okay, so there are some references here. So first people had to do the job algebraically, right? So Beckert and Merkle classified objects of DB in decomposables. Arnes and Laking and Paukstello, they classified all morphisms. They described the basis for morphisms between the decomposables, and then Chanakchi, Paukstello, and Schroll computed some mapping cones. And finally, Oper, Plamondon, Schroll gave this pictorial language, but it's closely related, very closely related to Haydn, Katsarkov, Kontsevich. And they say the following. So if we have a gentle algebra over K, then there is some surface, which is again with all these decorations, which is with, say, some green and red dots on the boundaries, possibly some red punctures. And if I want to record the grading, then also some configuration of red arcs, which cuts the polygon to polygon, the surface to polygon, such that each polygon contains exactly one green dot on the boundary. And in decomposable objects, in decomposable objects in the perfect derived category are either, okay, so what was blue is now green before. What was blue? Before I was drawing the arcs in blue, now they are green, so sorry for that. But non-trivial, so we have either so-called string objects, so these correspond to arcs which can self-intersect, but they should be homotopically okay, so they are considered only up to homotopy, so non-trivial homotopy classes of graded arcs, and non-trivial means that they should not be contractible to a point. Or we have bands. These should be some non-trivial homotopy classes of closed arcs, but with a band, I mean, you should somehow remember how high it lives in a tube. So it comes along with some automorphism of a finite dimensional vector space. So this is what I want to say with a finite length kx plus minus 1 module. And if the result should be indecomposable actually, then this finite length module should be indecomposable, and the arc should be somehow minimal. I should run just once around, not twice. Okay. And so there are some so there is some graphical dictionary like that. Indecomposable non-perfect objects, if they exist in DB, they correspond to arcs winding around punctures, either on one end or on both ends. Again, up to some kind of homotopy. So, okay, I just demonstrated this intuitively. So then what are homomorphisms? This is actually a good thing. Then we understand also homomorphisms between arcs in this graphical calculus, right? So if we have two arcs, they may cross. And we again draw them in such a configuration, in such a way, up to homotopy, such that they cross as few times as they can for topological reasons in the picture. And for each crossing, we have a graded homomorphism. The degree of the homomorphism is from x to y shifted by n, by some n. And this n, of course, depends where how the arcs are graded, right? And the crossing should be oriented. So I could have a crossing from F to G, or I could have also some crossing going back. So I don't know what color can I use. Maybe a red one. So we can have also across a map from Y to X. So if the arcs cross somewhere in the interior of the surface, so we have to really care in which direction we consider a crossing, because this crossing corresponds to two maps, either from a map from X to Y shifted to some degree n, or from this other direction, which corresponds a map from y to x shifted by 1 minus n. So there is some relation between the degrees of the two, right? So the crossing has some degree depending on the grading of the arcs, which I didn't explain completely, but to some extent, right? And so we cannot choose a random degree. And there is, if it's an interior crossing, so there is also a crossing in the other direction. And if two arcs meet at the green point at the boundary, we also consider this as a crossing. But then the crossing also exists only in one direction. Okay, so then there is always a map only in one direction. And you can actually, these crossings were translated directly to complexes. So you can really, there is even a dictionary, Opper, Plamondon, and Schroll. They give a very explicit dictionary based on some other papers of people who computed the morphisms algebraically. And so we get some explicit basis of maps, and this explicit basis could be translated to complexes, and we really see what happens. And we have these basic maps, these maps from this distinguished basics, and one also can consider mapping points of them, and these are also computed, right? So if we have a crossing, then we kind of discard the crossing, and we basically resolve the crossing, right? So we delete the crossing and we reconnect the arcs. So before, when there was a crossing, so we get such a result. And so after in the mapping code, an arc of the basic map, the arc can actually either these two pieces could be connected somewhere farther, or an arc could really fall into two pieces. And then the mapping code has two indecomposable summands. And if we have crossings at a boundary, then we just do this, right? And we just basically concatenate the arcs. That's it. Okay, so this calculus is quite developed. And this is all what I wanted to say about the calculus, about the surfaces and the graphical calculus. So if you have any questions, you can ask. And in the last maybe 18 minutes, I want to get to the main topic, how this all interacts with semi-orthogonal decompositions. Okay, so maybe I will go to that. So first, maybe I will remind what a semi-orthogonal decomposition is. Okay, so a semi-orthogonal decomposition is it's also known under the name Gauss-Field motion sometimes. So this is just a different terminology. It's something like a torsion pair in a triangulated category. So it's a collection of two classes or full subcategories, if you wish, closed under isomorphisms. And we want that there are no maps from the right to the left. Okay, maybe I should have added condition 0. So sorry for that. So condition 0 was that actually R and L are thick subcategories. Okay, so they are closed under suspensions and desuspensions in particular. Then there are no morphisms from R to L. And then for every object X, there exists a triangle of this form, where R is in R and L is in L. Okay, and this triangle is actually unique, and assigning X to R is actually a functor. The triangle is unique up to a unique isomorphism. That follows from the previous axioms. So my notation is a bit strange. Why R is on the left and L is on the right? Because the inclusion of R to T has a right adjoint. So assigning X to R is a right adjoint to the inclusion from R to X. So the inclusion itself is a left adjoint, and vice versa for L. So yeah, I mean, we have this in the paper written in this way because this is how some people considered it. So sorry for the mess. So the classes are ordered in a bit counterintuitive direction. Okay. And so the question was, if we have this surface, right, and then this graphical calculus, we understand the objects. So the question was what semi-orthogonal decompositions actually mean. And it turns out that this means really cutting the surface in pieces along some cuts. Okay. And so So this is actually the main result. So I will state it now. So this is I now didn't include the archive number, but it was in the abstract of the talk. So if we have a gentle algebra, and then we have the corresponding decorated compact-oriented surface. So this surface is actually an invariant up to homotopy relative to the decorations again in some way, in some intuitive sense. And then semi-orthogonal decompositions of the category of perfect complexes. They are actually in bijection with semi-orthogonal decompositions with all of DB. The algebra has infinite global dimension. And this corresponds to something which I would call bipartite cuts of the surface. Okay, and I want to explain what these bipartite cuts are. And probably I will not have too much time to talk about the proof. But yeah, actually the proof is more tedious, I guess. There are some. It's just using that we know the representation theory. So maybe I will try to explain the result and do proof with some sequence of lemmas, which is maybe not surprising, but it has to be ordered in the correct way. And what are bipartite cuts? So bipartite cut. So it's a collection of some arcs along which we cut, and the arcs have to follow some rules. Right? So a separating arc, I will draw it like that. Right? It's an arc is dashed to distinguish it from other type of arcs, and these arcs always connect a green arc, green dot with a red dot. And the other red dot has to be in the boundary. So it should not connect a green dot to a red puncture. This is out of the scope. This is not allowed for in this theorem, right? And I say non-trivial. And what is non-trivial? So non-trivial is that I mean, if we have a boundary, and on a boundary component, so there is a red dot and green dot next to each other. So what we are not allowed to take something which is homotopy to the boundary segment. So this is not allowed. This is precisely what non-trivial means, right? So this is forbidden. Okay. So this is what non-trivial means. And a bipartite cut, it's again, we consider a separating arc up to homotopy, and a bipartite cut is a collection of these separated arcs which do not meet, which are completely disjoint. They should not meet even at endpoints, right? And okay, so if we cut the surface along these separating arcs, so we get a collection of some surfaces which are actually of the same type as our original surface was. They are oriented, and they may have some red punctures, and every boundary component has some has some green dots and red dots on them, and they again alternate, right? If you think of it, if you cut a surface along such an arc, or which connects a green and a red dot, you get such a thing, okay? And a semi-orthogonal decomposition had a left and right part. So also it should be possible, this is why it's called bipartite, to label the pieces which are left from the original surface as left and right, and each piece should be either left or right. I mean, it cannot have two labels. It can have only one label. And from the point of view of every separating arc, the picture should look like that, right? If you have a separated arc, so the separating arcs are simple. So sorry, I haven't said that. They shouldn't intersect themselves. And on the left of each separating arc, if you go in the direction from the green point to the red point, you should see a piece which is labeled left, and on the other side, you should see a piece which is labeled right, right? So sometimes this is not possible. You should make clever cuts. Okay, an example. So I have something like 10 minutes, so I can illustrate this on some examples. So for example number 1, so what can happen, right? So I can, for example, take some n-type quiver, right? And now I need enough sufficiently bigger n. sufficiently big n. So maybe I can take, I hope A5 is big enough, right? So I have, the surface is like that. And then there are some extra decorations, either a line field or these red arcs, which I will ignore. And so what can we do? So I cannot cut this one, but I can, for example, have such a cut. And I can also, and now I should be, so this part then has to be, how is it? According to the rules, so if I go from red to, so this could be L and this could be R. But I can cut even more. I can, for example, also cut this. Right? And so these are, so I can have, so this is an example of a bipartite cut, right? And what is good, that really the left and the right, the pieces which are left from the cutting are really geometric models or these graphical models for the triangulated category L and R. So the triangulated categories L, these categories L and R in any decomposition, semi-orthogonal decomposition of a gentle algebra are again gentle algebras, but with two. There are two catches. First, these algebras are maybe graded gentle algebras. So the arrows of the, we also need to add some grading of the arrows of the quiver, and we consider the gentle algebra as a DG algebra, as a DG algebra with zero differential, and in this sense we consider the derived category. Okay. So this follows from Haydn, Katsarkov, and Kuntsevich. Or in an updated version of our paper with Jakub Kopřiva, this result should be there kind of down to the earth, computed explicitly, but it's also related to some work of Haibo-Jin and Sibylle Schroll. So there are some, it essentially could be extracted from the literature also now. And the second part, the second thing is you see this part R, there are two parts R, right? So if you look if you discard this L and just see what are the right parts. So there are two pieces. So what does this mean? This means that the surface will be disconnected. This will not be connected, right? So if I want to, so this falls apart to two disks. This will be the right part, and one disk, this will be the left part, right? And I have to draw the correct number of vertices. So we have 2 here, we have 3 here, and also draw this. And so this, so the corresponding category R will be really as a category. So R will be equivalent to dB. This would be KA1 times dB of KA2. This can happen. The category that the pieces need not be connected. And for L, this would be, so how many we have? We have, this would be again dB of KA1. And originally this was what? This was 1, 2, 3. No, sorry. This would be 1, 2, 3. So this should be A2. Now 1 plus 1 plus 2 is 5. So originally it was A5. So it should agree. Okay. So this is one example. What can happen? And okay, I can show you a little bit more complicated example, right? I can look at the Kronecker algebra. So there the surface was like that. So it was an annulus. And okay, so I need to draw the decorations again. And now, what can happen now, right? What can I do now? I can I can take a separating arc here, but this is not enough, right? Because I cannot label, if I just have one arc, I cannot label what is left to left and right pieces. So if I want a bipartite cut, I can, for example, add another cutting arc here, and then really this could be, I can separate the piece to two discs, and each of the two discs actually corresponds to L and R. They both correspond to dB KA1. So the derived category of the field, right? Just dBk. Okay. And you, of course, know, I guess, a lot of semi-orthogonal decompositions of dB of the Kronecker algebra. So this surface corresponds to 2 dB of the Kronecker. Right? Yes. So I'm a little bit ahead of time, but this is pretty much all I wanted to say. I'm not sure how much I should plunge into showing you a proof right now. Yeah, maybe I will finish a bit earlier because I don't have too much time to start anything substantial. So I leave some time for questions. So thank you for your attention.
So thank you very much for your very nice talk. Are there any questions or comments?
I have a very basic question. So, yes, so when you had the disk model for the path algebra, could you explain how you constructed non-trivial complexes from the R's?
So sorry, I have heard you not so well, unfortunately. The quality of the so what did you ask again? So how do you, if I have
Yes. Yeah, okay. Can you explain how to construct complexes from the
complexes from
R's?
arcs?
Yes, yes. Like I understood the projective modules and so on, but the complexes I couldn't follow.
Okay. So maybe I can I can look back at this picture, right? So I have this. I have the, I mean I can just maybe look at the left hand side of the picture. Okay. So
Yes,
I draw. I have this arc, this blue arc, which starts at the green point, goes around, and ends at the green point again. Okay.
yes,
So now I take a configuration. I take the arc up to homotopy in such a way, up to homotopy relative to the endpoints, such that it intersects these red arcs, which were a part of the decoration, as few times as it can, right? So that means in my case that up to homotopy I want to prevent things like this, right?
okay.
So this is not allowed, but up to homotopy I can get rid of. And once the arc is in such a minimal position, then I go around and I record which red arcs it hits, right? So if I go around, for example, in the counterclockwise direction, so I start here. Now it hits P2 once. So
Yes,
I record it here. So I mean, this would be, say, this P2 here.
yes,
Then I hit P1, so I record it, and then it hits P2 once again, right?
yes,
Okay, and so first I will draw something which I will call an unfolded complex. So because between this P2 and P1 there are some morphisms, and I haven't indicated the morphisms here. So there is, but essentially for Kronecker, I mean, there is no choice. You can draw this into the picture, but there is, if there were more arrows, we would have to keep track which arrow. But here there is basically exactly one basic morphism from P1 to P2.
yes, yeah, there's only
And
one mark.
so it has to go here, and also here we have only one morphism here, right?
Yes, yes,
So, but now I have a zigzag, not a complex. And how can I build a complex from it? So I will, for example, start with this P1 and I put it into some degrees. So for simplicity, say in degree 0, right? And if P1 is in degree 0, then each of these P2s have to be in degree 1. And I keep both of them.
Why is that? Why is then the P2s in degree 1?
Yeah, because okay. So what I want to do basically, I want to have a okay. So imagine that okay, let's say it like that. Let's say it like that. So the components of the complex will be direct sums of these projectives which I have here.
Yes.
And the maps which I drew here would be what? They would be the okay. No. Actually, there is not exactly one map. So I should have kept track, and I haven't explained that. So one of the map corresponds to alpha, one arrow, and the other corresponds to the other arrow in the Kronecker. Otherwise, I wouldn't get an indecomposable object. Okay. So this is something which I haven't explained well. But so I want the components of the complex to be direct sums of these projectives which I got in the zigzag. And the maps which I have in the zigzag, I want them to be components of the maps between the direct sums, right? So if I have a map from one direct sum to another, so it's actually a matrix of maps between the indecomposable components, and I want these maps to be there, right? And if I have such a requirement, then both these copies of P1 have to sit in degree 1.
Yes. Okay. Yeah.
Okay. And then what I do, I just add them together. So I take P1, I add these two copies. Sorry, this should be P2, and there would be a matrix, and one map would be given by alpha, and the other would be given by beta. So this will be the complex.
Yes. Yeah. Now it's
Yeah. So what I didn't explain very well, but I think you can either read it or if you make some experiments, you can see how this is done. Which arrow is which, right?
Yes. Yeah, yes. Thank you. Yes. And I had one more question. So, I mean, classically for the Kronecker quiver and let's say for the just the path the path algebra of the path graph or the algebra of upper triangular matrices, say equivalently, we have these combinatorial models of like Riemann, Christian Riemann, and so they have these combinatorial models where they start with, let's say, the path and make some sort of grade to so so for example, if you're looking at AN or let's say A5, that's the path, then there are these classical combinatorial models which they apply on the graph to get some kind of to get a grade, and then they take the free K-linear category and quotient it by the more standard Latin relations, and that also gives the module category. So I'm saying that those are the combinatorial models. So is there a way to connect those combinatorial models with these geometric models which you are talking about?
Yeah. So who are the authors of the modules? I understood Riemann and sorry, the sound
Yes.
quality for me is quite bad, unfortunately.
Sorry, no, yes. So, yeah, essentially, Christian Riemann in her paper on degenerations of quiver representations describes this combinatorial models, and she then uses it to prove some results. So, yeah, so I'm wondering if those combinatorial models, which exist essentially for finite representation type algebras, and in fact also for this for Kronecker quivers, is there a relation between those models and this?
So, well, finite representation type. So the I would have to check the models. So I'm not sure now. For the A type, it should be somehow straightforward, I guess, because you cannot do too much. D type algebras are not gentle. They are, I think, called Q gentle or something. There are also some extensions. This was studied, I think, by Igor Burban and Claire Amiot and Pierre Plamondon. So then the surfaces are not surfaces, but there are some kind of orbifolds. And I'm not sure what would happen with E, but in the first place, sorry, I cannot answer the question. I would have to check these models Maybe
Okay.
if you can send me an exact reference, or I will try to
Yes.
locate it.
Yes.
But
Yes.
thanks for the question. I will try to find out what exactly the relation is.
Yeah. Okay. Understood.
So are there any more questions or comments? And, I have one question. Is there some results about string algebra? Because I know for the module theory, recently there is some geometric interpretation of the indecomposables for the string algebras, but for derived category, I don't know. Is there some?
I don't know, because when I asked the question, people who work on that before for a long time, like David Poxello, they told me that the main problem is that string algebras are not derived tame in general, right? Because gentle algebras are derived tame, and then you have just strings and bands and nothing else. But string algebras can be derived wild, so probably you can capture only something. But I don't know. I mean, this if there is any ongoing work on that.
And the other question, in your direction, you cut off the means the geometric model to the smaller one. But in vice versa, if gluing the small piece together.
That's an interesting question. I haven't thought of that, but of course there would have to be some restrictions to get a gentle algebra again. But why not? I think to some extent this is done in a very fancy way by Merlin Christ. Because they're gluing, basically this model for gentle algebras is always kind of obtained by gluing some polygons. And polygons correspond to Dynkin A-type quivers. So I don't know, maybe with their technology it's possible to do it in a very fancy way. But yes, that's a good question. It could be maybe done really again in some down-to-earth way.
I think the important question is that is for any gentle algebra, it is possible to construct by gluing the good pieces. I mean, for example, from type A.
So basically, yes, okay. How is it? It should have been then related to these polygons. Yes. So quite often it's possible, because quite often it has some composition series by basically via this longer semi-orthogonal decompositions where the pieces are derived categories of a field. This happens. This is a work of Sibylle Schroll and I think Haibo Jin or Wei, one of her co-authors. Now she has quite a lot of papers. I would need to check which one. So they say that for almost all surfaces you can actually glue it from derived categories of a field. It has a silting object. They say it has a silting object, which basically means this, but there are some strange examples where you cannot do that. So I think the smallest one is this number 4, which I have here, but there is just one green point and one red point on the boundary component. And this should have no semi-orthogonal decompositions. Yes, so there should be some exceptions. There should be some derived simple algebras which cannot be glued from something simpler via semi-orthogonal decompositions. But the answer should be basically in paper for Sibylle Schroll and her co-authors.
So thank you.
Okay, thank you too.
Are there any more questions?
I had one more question. So I was so I'm comparing your semi-orthogonal decompositions with those that appear in, let's say, algebraic geometry. And if I use the fact that the bounded derived category of Kronecker cube is same as the derived category of coherent sheaves on projective line on T1. So now the semi-orthogonal decomposition which you gave cutting the annulus, does that correspond to the classical decomposition of the structure sheaf, comma, the twisting sheaf twisted by one?
Yes, exactly. These two pieces, two derived categories, there are not so many. So yes, exactly. So I think these are actually they should be actually the only non-trivial ones. What you can of course do is take some modifications. I mean, you can kind of rotate this, right? So you can get different decompositions. So it again has to do. You can also have cuts like maybe I just temporarily draw it in the picture. You can have cuts, for example, like that, and yes, but exactly. I mean, this should be those which you just told about, where you really L is just the additive closure of shifts of some twist of the structure sheaf, and then you have the subsequent twist of the structure sheaf.
Okay.
Are there any more questions or comments? If not the case, thanks to speaker again. Thank you very much.
Okay, thank you for giving me the opportunity.
Thank you. And if it's possible, please send me your notes for putting on the web page of the.
Yes. I will do it.
Yeah, thank you.
Okay. I just need to stop sharing it because it will be easier for me to click where I should.